So the basic definition you have for the word continuity as it relates to functions is that a function is continuous wherever you can draw the graph without picking your pencil up off the paper. And that's basically right. That's not a very mathematical definition, however, and now that we have the idea of limits, we can actually define the word continuity. So at some point x equals a function is continuous if the limit of the function at that point, the limit as x approaches a to the function, just equals the value of the function there. So imagine you're looking at a table of values and they're just a bunch of decimals that are close to each other and they just proceed in a way with no holes or jumps or asymptotes, then that's what a continuous function looks like. So it's just smooth. It just doesn't have, if it has a hole or an asymptote or a jump, or it's not defined at all, then it's not continuous at those points. So we have to be a little finicky here. This definition really relies on three things. It requires that the function is defined. So like a square root function, if it was like the square root of a negative number, obviously the function is not continuous there because it doesn't even exist there. It requires that the limit exists. So, you know, we talked about the cases where the limit wouldn't exist, like at a hole or at a jump or an asymptote. It wouldn't be continuous there because the graph breaks. And then it also requires that those two things are the same thing. So you could have the function being defined, you could have the limit also existing, but you could have them not agree, as we're going to see in the next example. So this is an example of the type of problem that you're going to see on the exam. I'm going to ask you to identify the discontinuities, which is easy. It's just any of the places where something weird happens, right? You see 4 of them right off the bat. But when I say why the function is discontinuous there, I specifically want you to contradict the definition of continuity. So I want you to say something about the limit or the value of the function and what about that makes it not continuous. So for example, the first one we see off the bat is x equals 1. There's a hole at x equals 1. So the limit does exist there. It looks like the limit is 5, right? The limit can still be there if there's a hole, but the function is not defined. So that's really all you would have to say. If you just say f of 1 is undefined, that breaks the definition. So here's a very thorough answer. At x equals 1, the limit is fine. The limit appears to be 5, but f of 1 is undefined, right? So it can't be continuous if the function has no definition. Moving forward at x equals 3, there's a jump in the graph. That is, in fact, what we would call a jump discontinuity. I don't need you to know the names of the various kinds of discontinuities. I more need you to know, why it's not continuous as it pertains to the limit. So the function is defined. F of 3 does appear to be 1, right? Because that dot is filled in. But the limit coming from the left is 1, and the limit coming from the right is 2. So that means the limit as x approaches 3 of this function does not exist. So really, that's all you'd have to say. The limit doesn't exist there. Right, so if you're being really thorough, you'd say, okay, f of 3 is fine, f of 3 is 1, but the limit doesn't exist. You wouldn't have to tell me why. If you wanted to say that it's different coming from one side rather than the other side, that's great, but this is perfectly sufficient. Okay, now at x equals 4, we see that weird hole where the function's defined elsewhere. So we're close here because f of 4 is 5, right? So the function's defined. The limit as x approaches 4 appears to be 3. So the limit is also defined and the limit exists, but 3 is not 5. Those two things are not the same. So what you would say is the limit as x approaches 4 of the function does not equal f of 4. Right? You wouldn't even have to say this much. Just say the limit, the values of the limit does not equal the function. So just say f of 4 does not equal the limit as x approaches 4 of the function. And then at 5, that dashed line indicates a vertical asymptote. So there's all kinds of stuff you could say here. Don't just say vertical asymptote, because that doesn't pertain to the limit or the definition. Say, well, the function's not defined, right? It's obviously a vertical asymptote. We're dividing by 0 or something. So that's enough. The limit's not defined. That's like called an infinite discontinuity. The limit doesn't exist at a vertical asymptote. Or you could say both of those things. All right, so that's it. You don't even need both of those things to have it be discontinuous. Either one of them would do. Either the limit doesn't exist and the function doesn't exist, so it's super not continuous anywhere you see a vertical asymptote.